Welcome to my Eurographics 2021 talk, Deep Detail Enhancement for Any Garment. I am Meng Zhang, a postdoctoral researcher at Smart Geometry Processing Group, University College London. I co-authored this paper with Tuanfeng Wang, Douglas Lin, and Niloy J. Mitra. Achieving high-quality and robust physically based clothes simulation is difficult. It is computationally expensive, tedious to set up, and can be unstable when the quality demanding increases. For example, when simulating with higher mesh resolution, the blue dress breaks the constraints enforced by the yellow belt. By using a constant version of the garment, the coarse geometry is easily simulated efficiently and reliably. However, the detail wrinkles missing is the most shortage of the coarse simulation. Therefore, in this work, we present a deep learning-based method to synthesize plausible wrinkle details on a coarse garment geometry, and our method generalizes across garment variations and body motions. There have been various efforts to augment coarse simulation output with fine details, using various approaches including optimization, data-driven, and learning-based methods. However, none of them developed a universal pipeline that enables generalization across different garment types, sewing patterns, and motion sequences. In this work, we present a deep learning-based method that enhances an input coarse garment geometry by synthesizing realistic and plausible wrinkle details. The goal of our work is to enable the generalization across a variety of unseen garment types, sewing patterns, and motion sequences. As garment undergoes motion, its global shape can be consistent across different resolutions. The fine detail wrinkles of the high-resolution garment appear in the same region where sufficient cues to hallucinate high-frequency wrinkles are also provided in the coarse geometry. We hypothesize that, given the coarse geometry of a garment, the dynamic detail wrinkles can be learned from many such local patches observed from different types of garments undergoing different motions. Besides 3D meshes, another geometry representation is 2D normal map. We downsampled the high-resolution map to the coarse version, which has region correspondences with a high resolution and similar texture patterns as a low resolution. We assume that both the coarse normal map and the downsampled normal map fall into the same distribution. If there exists a function to transfer the downsampled normal map to the high resolution with fine wrinkles, we are able to transfer the low-resolution normal map to the same distribution of the high resolution with the same function. The fine wrinkles are generated either by sharpening the original coarse folds in the downsampled normal map or synthesized conditioned on nearby coarse folds. Now we consider the detail wrinkle enhancement task as to find two distributions that respectively represent the low-resolution and high-resolution normal map and to formulate the transfer function. The recent success of image-based artistic style transfer methods give us some significant inspiration. A per-stage image is produced by feeding a content image through the style transfer network. The two images, along with a style image, are passed through a pre-trained VGG network. The resulting intermediate representations are used to compute the content loss and style loss. The content loss aims to ensure the content from the content image is kept in the output image, while the style loss enforces a gram matrix similarity between the output and the style image, which is helpful to synthesize style patterns guided by the style image. Inspired by the style transfer approach, we cast our problem as the detail transfer across the normal maps of the garments. With a low-resolution normal map as input, our detail transfer function produces a normal map that is expected to have the same detail quality as a high-resolution normal map, meanwhile to maintain the coarse folds as the input. We pass a low-resolution, high-resolution, and generated result normal maps through the VGG network and compute the content loss and the style loss. In our work, the content loss aims to maintain the original coarse folds from the low-resolution normal map, while the style loss aims to synthesize detail wrinkles that are similar to the high-resolution map. The pipeline of our work starts from a coarse garment geometry. We represent 3D geometry as a 2D normal map. The core of our method is a detail enhancement network that enhances local garment patches conditioned on the material type. We combine all the enhanced normal patches to generate the complete normal map that captures fine wrinkle details. In case the garment material is unknown in advance, we present a classification network to predict a one-hot vector to indicate the material type. Finally, we lift those wrinkle details to 3D geometry. We adopt UNet architecture for our detail enhancement network. The encoder projects the input normal map into a latent space. The latent representation is then used to construct the output normal map by the decoder. Although garments made of different materials may share similar coarse geometry, the fine details can vary conditioned on the material. We designed the decoder using conditional instance normalization to adapt for different material types. Specifically, given a material type theta, the activation of the layer I is xi. We shift and rescale xi to get zi by the learned mean vector and the standard deviation computed based on the material type. The detail enhancement network aims to transfer the detail patterns from the high resolution to the low resolution normal map. With the detail transfer function inspired by the style transfer task as we have introduced before, we employ the content loss and the style loss to optimize the network parameters. In case a material type is unknown, we present a classification network to predict a one-hot vector to indicate the material type. The material classification system is composed of the pre-trained VGG network and 4 fully connected layers. We crop patches from the coarse normal map. The cropped patches are first embedded to be flattened feature vectors by VGG as the input of the following fully connected layers. The output of the material classification is a predicted material probability with a dimension corresponding to the number of the materials captured in our datasets. For each material type in our dataset, we plot the histogram of patches based on the probability of them belonging to that material. As an example shown here, material 1 has the highest distribution among the 5 materials, and we got the one-hot material vector 0, 1, 0, 0, 0. We trained the classification network by using cross-entropy laws between the predicted probability and the ground truth material type. We train our network using 3 datasets, specifically a piece of hanging sheet, a long skirt, and a pleated skirt, in order to generalize our approach across different 2D parameterizations. We adopt a patch-based approach. Instead of operating with complete normal maps, we use patches cut from the normal maps as input and output of our network. In order to ensure coarse and high-resolution patches are aligned during training, we generate the input to our network by downsampling the high-resolution normal maps. Once a network trained, given an input normal map obtained by running a coarse simulation, our network produces a result that is close to the ground truth run by a high-resolution simulation. Now we validate our method in terms of gram matrix distribution of the output features of VGG19 layers that we used as style layers. We find that the coarse normal map as input used at runtime and the downsampled normal map as input during training share similar feature distribution as we hypothesized before. The patch style features of the high resolution are distributed in another region. Our transfer function is able to transfer the style features of the coarse normal map to the same distribution of the high resolution. Once the enhanced normal map is calculated, we finally lift the details into 3D geometry. Since coarse geometry is known, one common solution in the CG industry is to bake the normal map onto the original coarse surface during rendering. While we can also adopt the normal map-guided 3D deformation to generate the final 3D garment geometry with fine wrinkles. For the method details of the 3D deformation, please refer to our paper. Here we show some of our results. For the coarse geometry produced by skinning-based deformation, we use a baking method to enhance our generated details to the geometry surface. The coarse geometry can also be generated by running the simulation with a low-resolution version. In this case, we lift our generated details to 3D geometry by the method of normal guided deformation. Here is another result. In our experiments, all the garment types, styles, sewing patterns, and motion sequences are totally unseen during the training process. Here we show examples of garments made from different materials undergoing the same body motion. Our method is able to generate plausible details in all cases that will respect the input coarse geometries. We trained and tested our method with different material parameters under a universal framework. In summary, we have presented a deep learning-based approach to synthesize plausible wrinkle details on coarse garment geometries. Our system is mainly composed of the material classification network and detail enhancement network. Our approach draws inspiration from the recent success of image artistic style methods and casts the problem as detail transfer across the normal maps of the garments. We enable our method to generalize across different garment types, sewing patterns, and motion sequences. Our method shows impressive generalization capability, but it still has several limitations and it triggers some future works. Here, we list 3 of them. First of all, in order to generalize a detailed enhancement network across different materials, we provide the material parameters as input. Hence, at runtime, the network can be tested only on material types and have been seen during training, generalizing our method to unseen materials, for example, by learning an implicit material basis, is an interesting future direction. Secondly, in our current implementation, the coarse garment needs to be simulated case by case. A possible future approach is to run simulation on just one common coarse garment shared by all garments of the same type. The style-specified details are syntheses based on the coarse garment motion shapes. The third one is controllable wrinkle synthesis. Wrinkle brush is a fashion industry tool to draw style-specified wrinkle patterns on the garment surface. However, the wrinkles are drawn at a still state and unable to vary along with the garment motions. In the future, dynamic wrinkle authoring is worth exploring to synthesize dynamic wrinkle patterns which can vary along with motion frames. That's all. Thank you for your attention.